Good morning, everyone. Welcome to the second day. My name is Amit Ghosh, and I'll be chairing this session. It's a great honor to be here to celebrate the contributions and achievements of TVR through this very exciting discussion meeting. The first talk today is by Professor Hide Takagi from Max Planck Institute, Stuttgart, and the title of the talk is Heavy Fermion Oxide, Lithium Vanadium Oxides with New Surprises in Store.
Yeah. Can you hear me? Okay. So good morning, everybody. And I feel very much privileged to be here on the special occasion for Rama. And more than 40 years ago, I became a graduate student, joined the group of Shoji Tanaka in Tokyo. And at that time, they are working on the question of whether tantalum disulfide mode or Anderson insulator. And my first task as a graduate student was to read this historical paper, Gang of Four. That's why you became my hero. But 8 years after, I was lucky. I could have joined the AT&T Bell Labs, in New Jersey. And this is Bell Lab. And I was in 1 year and somewhere here. But somehow, I found that, my hero, Rama, is nearby me, somewhere here. And I kind of realized that you are a consultant of AT&T Bell Lab between 90 and 91. Which completely overlapped with my stay at Bell Lab. And at that time, we are crazy about ITC Q plate. And I still remember, we discussed the linear relativity, absence of the desaturation, unusual Hall effect. And I was very happy actually, the big name that like Rama listened to, poor Japanese, postdoc, like me, kind of for long, this kind of physics, I really felt, privileged to discuss with, Rama. So thank you very much, for your discussion, intuition, and happy 886, birthday. And since this, Bell Lab period, somehow, I have been working on, Oxide business, over 40 years, I was lucky. And I have been exploring, exotic, phase of correlated electron, like electron, solid, liquid, gas, or sometimes superfluid, superconductivity, liquid, crystal. And of course, often spin degree of freedom, orbital degree of freedom, charge degree of freedom, they behave independently. And then we can have, spin liquid, orbital liquid, and that's kind of my case. And if, there were, any kind of guiding principle for my exploration, I kind of emphasize that, my kind of guiding principle, make, electrons, unhappy, then they do something exotic, crazy. And my keyword to make electron unhappy was, confinement in low dimension, bring frustration, competing interaction, quantum criticality, multiple degree of freedom, bring high entropy, unusual valence state of ion. And today, I'm going to speak about the specific compound, which I worked on over more than 30 years, because this compound contains 4 out of 5 keywords. And this compound was established as the very first oxide in heavy fermions, around 2000. And since then, there was kind of a very long mystery. What is the origin of heavy quasiparticle formation in this compound? And today, today I want to kind of submit, my kind of answering sheet to this, question based on our recent experiment. And my answering sheet was based on a collaboration with those, people, from Max Planck, Stuttgart. And in parallel, I had the kind of intense discussion with those theorists group, Ryotaro Aita and Antoine George. So yeah, I know you hate crystal structure, for the talk over TD yesterday, but because of that, let me educate you a bit. And first of all, lithium vanadate crystallized in a spinel structure. And maybe if you know sodium chloride structure, you can easily construct, so-called spinel structure. So like this is a sodium chloride structure of, vanadium and oxygen, very simple. And you find the vanadium from a tetrahedron inside the cube. And just, pick, vanadium oxygen cube, connected by vanadium corner like this. And then you see network of, corner shell tetrahedron. That's nothing but the pyrochloride lattice. Okay. And this is LiV2O4 lattice, strongly frustrated, easy. And lithium is located here, surrounded by 4 oxygen here, tetrahedral type. Okay. And you see vanadium here is coordinated with 6 oxygen, so they are in an octahedron. So octahedrally coordinated. And just counting in a balance, lithium is 1 plus, oxygen 2 minus. Because of an odd number here, they have half integer balance, 3.5 plus. So, or in other words, we have 1-to-1 mixture of vanadium 3 plus and 4 plus, 3D2 and 3D1 on geometrically flustered lattice. And the situation is very similar to that of magnetite, iron 3 or 4. Okay, so the B site iron has 2.5, okay, 1-to-1 ratio of 2 plus and 3 plus. And this compound is metallic, down to T equals 0, no charge ordering. There are only 2 spinel oxide known to be metallic down to T equals 0. One is lithium vanadate, and the other lithium titanate, which is 14Ka superconductor, ECS superconductor. Okay, so here is a summary of a physical property of lithium vanadate. Okay, and there is some like 20, 30K, and that indicates transport became coherent below that temperature, and at low temperature you see a beautiful T-square dependence down to T equals 0. And more importantly, specific heat coefficient gamma is as large as 400 millijoule per mole square, comparable to cerium, uranium, heavy fermion, intermetallic. Yeah.
Very small residual resistivity.
Actually, I'm gonna say it's not small. Yeah, yeah. Small is past let me say 1 micron.
Copper standard.
Yeah, yeah. Oxide standard. Yes, yes. Okay, and like in a famous Kadawaki Woods plot. Okay, lithium vanadate kind of here, and they can satisfy Kadawaki Woods rule. And they are located somewhere around the cerium compound, uranium PP3. Now they can look at susceptibility. Okay, so at the height you see a Curie-wise behavior with spin moment close to spin 1/2, and at low temperature susceptibility is almost constant. And with this T equals 0 susceptibility and the gamma, we estimate Wilson ratio of 1.7. So it's clear it is correlated ferromagnetic. Okay? And below 20, 30K, we do see a large temperature dependence of Hall effect like this, and which I will discuss later. And here is band structure of the vanadate. And as I said, vanadium is octahedrally coordinated, right? So and because of octahedral coordination, they do split the EG and the T2G. Okay, Trivedi T2G, and this T2G orbital contains 1.5d electron because it's 1-to-1 ratio of 3d1 and 3d2. And in reality, there is a small trigonal distortion on top of octahedron, And the trigonal distortion splits the T2G into doubly degenerate EG prime and A1G inlet. And if you take a look at boundary calculation, so those red come from A1G character, and those blue come from EG prime character. Okay, so you see a clear separation of the character, and the EG prime look like tight binding pyrocolor band. You see a flat band and two upper and the lower broad band for pyrocolor tight binding band, and this blue mimics tight binding pyrocolor band. But of course, this is EG double degenerate, so they are double degenerate. And there is a A1G character somewhere, but they form a very narrow band, over the order of 0.5 electron volt only. But it doesn't mimic the pyrocolor band. Perhaps A1G pointing towards center of the tetrahedron overlap much less with their neighbor, and power zero higher order hopping plays very important role for A1. But anyway, you can see some local character of A1G derived band, and plus broad pyrocolor EG band. And so this is country picture of band picture I showed. And in a pyrocolor lattice, okay, primitive cell contains one tetrahedron. So that means you have 4 vanadium in primitive cell. Right? So I said we have 1.5 d electrons per vanadium, but we have 4. That means we have 6 even number of electrons in the primitive cell, and that's quite important. Actually, we long dismissed that point. Okay, so like 6 electrons fill up 12 T2G band. 3 times 4 equals 12. And as I said, those lower EG prime band, it can doubly degenerate, so it contains 4 electrons. So like first 4 electrons occupies the lower EG band. The remaining 2 occupies upper EG, but upper EG overlap with A1G, and therefore it should be a kind of semi-metal. And in fact, band calculation predict, anatomic, A1G is kind of hybrid, and they're giving small, metallic Fermi surface, containing roughly 0.1 electron per vanadium. Okay. Now, of course, the question is, why such d electron only system, metallic system, so heavy Fermi state, analogous to 4F condor system? That was, my question. What is the mechanism behind? That I would like to discuss today. And in fact, at low temperature, they behave like condor heavy film, as I showed before. But take a look at the high temperature, they really, look like other correlated 3D transition metal oxide, correlated transition metal. For example, like high temperature resistivity is metallic. But as you see, let's say like 1 milliohm centimeter, it's actually beyond the Yoshiliga limit. So actually, this looks like metallic, but it's not really metallic. This is kind of incoherent transport. And if you do see like optical conductivity, okay, around this temperature, you don't see any Drude response in optical conductivity, just broad. And with lowering temperature, Drude-like component growth. So the system is getting a kind of coherence, on cooling. And this is in marked contrast with 4F heavy Fermion system, like cerium uranium compound. They do show kind of a saturation around 100 microseconds. And of course, often they show condor logity, but we don't see N. So in that sense, it looks like a really, a Bhatt metal behavior of transition metal, correlated transition metal oxide, like a cupellate, luteinate. And theoretically, there are 2 camps, condor camp and Mott, camp. And early days, Anisimov, said, this compound can be mapped onto condor physics. And his reasoning is this A1G band, I showed, is, very narrow, like half electron volt. And introducing a Coulomb nu, they split into lower Hubbard and upper Hubbard band. And the lower Hubbard contains one localized spin or half-inner moment. And the remaining 0.5 electron occupies the EG band. So like you have, conduction electron and the localized moment due to correlation effect on A1G. And he discussed that there could be a miracle condor coupling due to cancellation of ferromagnetic exchange and anti-ferro super exchange. Yes. Of course, like if you take a look at susceptibility, at high temperature, I do see a Curie-wise behavior, and of course, like neutron inelastic scattering, they do see some, strong, spin fluctuation. So in that sense, it's there, yeah. But my point is, yeah, the difficulty is everybody kind of criticizes this picture because having a condor coupling, they need the miracle cancellation, and many people didn't believe it. And here, propose, something like because of A1G and EG, they behave like condor insulator, and because we have 1.5 d electron. So he said, yeah, carefully here, 0.5 hold off to condor system. But somehow, I was a bit puzzled about his statement because, as I said, we have even number of electrons 6 instead of 1.5 in the primitive cell. And, this kind of a doped, picture, might be good and bad, I had some, question. Maybe let's on the other hand, my old colleague, Arita, said motonets is kind of a basis for heavy fermion behavior. So I think it's a similar story, like, Anisimov. They said, A1G split into upper Hubbard and the lower Hubbard. But it's not, orbital dependent mode. But they said, this state is 0.022, 2% hold off, motor state, and creating a sharp, quasi-particle in-gap, state at the Phillips level. And they said, that's the origin of, heavy fermion. So it's a kind of doped motor issue. That was, their picture. And they said, A1G EG coupling doesn't do anything, and they ignored the EG. However, I was, a bit, curious, whether we can neglect, role of EG band. Because, if, EG band, contribute, we should see some contribution from light mass carriers, right? But since, we saw, this Kadowaki-Woods, relationship for T-square resistivity very well, and that means, all carriers are kind of heavy. And that's kind of one point. And also, because of mixed balance, like, magnetite, we do expect charge ordering instability rather than, more, criticality. So those are kind of my question mark. And that was in my mind, for long, and I occasionally revisit this, compound. And recently, I revisited it again, and I come to kind of some, conclusion, I believe. And in a real space, we could have shown the system is a failed charge order insulator, and all that kind of blocked by geometrical acceleration. And in K space, we kind of realize that it is a really same metal with extremely heavy electron and holes through very likely Wundt coupling of EG and EG and the localized N1. And of course, this hole and the electron are subject of charge ordering instability in real space, but because of geometric frustration, they avoid ordering. That's kind of my scenario for the heavy fermion state of this compound. Let me begin with charge ordering instability. Okay, so charge ordering was kind of first discovered in the magnetite, iron 3 or 4, 1-to-1 ratio of iron 2 plus and 3 plus, and Fermi, yes. Oh, sorry. Yeah, Fermi, proposed that this poor metal to insulate that transition around 120 K, called the Fourier transition, is due to charge ordering. And he proposed the charge ordering pattern stack over 2 plus and 3 plus along 0, 0, 1. But actually, charge order pattern was found to be not Barway, but quite complicated stuff. But Phil Anderson came into this business long ago, and he didn't get a charge order, but he was kind of curious about why this Bhatt metal region spreads over wide temperature range. He questioned that. And his answer was, it is some kind of a charge liquid, due to geometric fluctuation. So iron 2 plus is, due to charge neutrality, can be regarded as, minus 0.5 electron. And the 3 plus is 0.5 hole in real space, right? And of course, the positive and negative charge, try to attract, each other. So they, electron hole, 2 plus and 3 plus, would like to sit next to each other. But because of this tetragonal geometry, okay, they can make all the bonds happy, like a magnetic case. So what they can do is total spin 0 in case of magnetic case. In case of charge, total charge equals 0. This is called the Anderson condition. And then, of course, as you know, there are many ways of satisfying this Anderson condition. There are macroscopic degeneracy that profit selecting a specific charge order state as a ground unique state. So like ordering suppressed and some kind of a charge liquid state spread over the wide range. And you said that is the origin of Bhatt metal region. Now, lithium banerjee is a 3 plus 4 plus analog of magnetite. But magnetite, eventually find a unique charge order state, Fermion order below 120 K. But lithium banerjee, unlike magnetite, so no charge order. So our kind of working hypothesis is if system remains kind of entropic charge liquid with macroscopic degeneracy of different charge order state, is that kind of heavy Fermion state. And if so, many different charge order state kind of nearby heavy Fermion state. And if we give them some perturbation, for example, strain, because charge ordered object is an isotropic object. So if I give a strain, that on a couple with specific charge ordered state, and we can select one specific charge ordered state. Right? That was our idea. And so I strained them by using a kind of a thin film, and we prepared the 2 substrates for lithium banerjee thin film. Strontium titanate, matching each horrible, and they just relaxed, and they show the same lattice constant to bulk lithium banerjee. But if I put it on magnesium oxide, matching is only 2%, tensile strain. Okay, yeah. And they do kind of grow epitaxially. And we measured the resistivity and relaxed in a film with the same lattice constant as bulk thin crystal, so heavy Fermion behavior, no doubt. But going to strained in a film, okay, although film quality kind of better than this one, somehow we do see initiating behavior with activation energy of 50 millielectron. Look like insulator, perhaps charge ordered insulator. And we try to look for signature of a charge ordering using a STEM microscope with atomic size EOS function. So like here is kind of lattice, and we can check balance of vanadium from atom to atom using this yield spectrum. And we found that along this line, balance range is 4 plus 3 plus 4 plus 3 plus, and along this line 4 plus 3 plus 4 plus 3 plus experimentally. And this without any doubt gives a charge ordering stack of vanadium 3 plus and 4 plus 3 plus 4 plus along 001 direction perpendicular to film plane. So after 80 years, Fermi returned back to the scene. And of course, it is a stack of 0.5 minus 5, and the same charge expel each other. So like it's natural to have tensile strain stabilize this Barwell type charge So at least one charge order state nearby heavy Fermion state. Now we prepared a different kind of substrate and try to see what's happening. For example, instead of 001, magnesium oxide, we put 111, the kind of substrate, magnesium aluminate, and then we saw different kind of charge order, 111 charge order. We apply hydrostatic pressure, and we find another type of 111 charge order structure. So at least we find 3 different charge order structure. So I cannot claim macroscopic degeneracy, but at least we saw 3. And we believe, we found, hidden degenerate charge ordered state. And of course, it witness real space, charge ordering instability. So it is failed, charge ordered insulator. Now, next, question we wanted to ask is any signature of, charge ordering instability in K space. And to do so, we revisited low temperature transport again, quite recent. And the first thing we did was simply measured Hall effect and the G-big effect, down to 100 millikelvin. What we found was, well, this is Hall effect, and this is G-big effect, time plus, time minus. And they are, strongly temperature dependent. So apparently, we have both electron and hole. Okay, yeah. And in particular, suppression of a G-big is quite significant at low temperature. It goes almost 0. And taking a T-linear coefficient, okay, T-linear coefficient go to 0. So there is a very strict cancellation of electron hole contribution here. But of course, it's not surprising. As I said, from band perspective, we have even number of electrons, 60 electrons. So it's natural to have semi-metallic, equal number of electron holes. Right? Now, assuming number of electrons equal to 4, okay. So these observations tell us, first suppression of Hall effect means Hall effect is difference between the Hall mobility and electron mobility. So electron mobility and the Hall mobility must be close to each other. But that's kind of obvious. And the G-big effect is a weight, mobility weight average of G-big effect. So therefore, it is roughly difference between the Hall G-big and the electron G-big. And that goes to 0 means their mass is almost the same. Again, we have both electron and Hall, but they have the same mass, okay? Almost the same mass. And of course, that's quite consistent. Okay, they follow quite well Kawasaki with kind of relationship, and no short cut, by light mass carrier. So equal mass. And the last point, I want to make is actually related to magnitude of the kind of resistivity. And first of all, we do see a kind of quite metallic behavior. So to have that kind of metallic behavior, we need a mobility of at least 10. And the whole mobility is like a difference between the 2 mobility, and this is 4 to 8. So mobility must be much larger than 10, right? But our residual resistivity is roughly 20 microohm centimeter always. And this is kind of a high as very metallic system. But to have such high resistance with metallic conduction, to have such high mobility, our carrier density must be small. And this gives us some kind of constant of carrier density, roughly 0.1 electron per vanadium, consistent with LDA calculation. In fact, if I assume equal number electron hole, 0.1, we can reproduce Hall effect and resist kind of very well. And we see kind of a reasonable temperature dependence of kind of mobility. up to 40, 50. So it looks like we have small Fermi half. So now, this is, what, we obtained, from transport. So like we started from this band, and somehow, we found that extremely heavy, equally enhanced electron and the hole at low temperature. And somehow, they form a relatively small Fermi surface, 0.1 electron per vanadium. So they seem to maintain, LDA Fermi surface. Okay. Although, I have to say, because we have even number electrons, we don't have to satisfy Latimer summary, but somehow they respect LDA band calculation. So, mass is, as large as 100. And of course, those heavy electron mass should be subject of charge ordering instability in their space, but no ordering due to geometrical fluctuation. That's kind of our scenario. And maybe, at the end, let me discuss, kind of further. That part a bit kind of speculative. But, so we came from here and reached, here at low temperature. Maybe, let me consider like effect of correlation onto LDA band. And if I put, correlation virtually, pretending as if I'm theorist, then this is going to split narrow AYG band into lower Hubbard and upper Hubbard band. And of course, this, lower Hubbard, contains, 1 electron per vanadium. That is 4 electrons. So we have, 4 here. And the remaining 2 go to lower EG prime band. Okay. And since this band is doubly generic, so we have a half used Fermi surface for EG. But of course, at the end of the day, we observed, small Fermi surface, right? So to have small Fermi surface, there must be a big change in the kind of Fermi surface from this, line picture. And we believe this, comes from a coupling between A1G, localized zero moment, and EG itinerant electron. I'm not going to say condom, but some coupling produces small Fermi surface quasi-particle state. And with that, I think, we can understand that, most of the basic, property of that. Because at high temperature, if, those EG electrons kind of decoupled from a localized zero moment in A1G, we have, spin 1/2, localized moment here. And we have kind of big, Fermi surface. And at high temperature, we do see a very small Hall effect, indicating a small Fermi surface, large Fermi surface, and Curie-wise, behave. And transport is quite, incoherent. At low temperature, they become incoherent and form, small surface. Heavy semi-metal state is kind of produced. And at the end of the day, yeah, I kind of, come to, my kind of theory colleague and show data. And they did, state-of-art, DMT calculation. So Arita kind of updated kind of his technique. And, two group, group of Arita, Antoine George, they kind of both, kind of reproduced that, okay, this is 10 millielectron, so very narrow, okay? But a miniature of LDA band, around the Fermi level, and, showing a small phase surface in the metallic, state, okay? Consistent with, what, we observe. On top of that, Arita changed kind of temperature from low temperature, 30K to 70K. And those, heavy quasi-particle band, electron hole disappeared. And you see only big Fermi surface, coming from E prime G. So there is, coupling, decoupling, kind of crossover, between these two temperatures. Okay, so that's kind of fully consistent with the application. So this is my kind of answering sheet. And lithium Banerjee is kind of a semi-metal, which electron mass of maybe 200 to 300. And we have both electron and the hole, and that was kind of produced by coupling between local A1G and itinerant EG. And this part, I don't know, but according to my kind of theory colleague, the coupling, come from Hunt. So that's kind of quite different, from Kondo. And those heavy, electron holes are confronted by charge ordering and instability. But long range ordering is kind of blocked by geometry frustration. That's kind of my, maybe I just, put the, future perspective and finish my talk. Thank you very much for your attention.
Let's thank Professor Takagi for a very exciting talk. So the session is open for questions. So may I go to Sandra?
So as I understand, if I go to somewhat higher temperature, the picture is that you have fluctuating spins, but the charge configuration is also fluctuating.
Yeah.
Right. So presumably there's a big entropy coming from both the charge configuration and the spin configuration. And so I wonder if there's any evidence for this charge entropy. If you measure heat capacity in a field, and presumably you can remove the spin entropy. Right? You still have a large remaining entropy or more.
Yeah, it should be, yeah. So at the moment, my reason only coming from, strain-induced, static, order set. Of course, above that, we should be able to see some signature of, charge kind of frustration. And perhaps, we should go, say, like X-ray inelastic scattering, to see, the kind of charge, correlation. Yeah, that actually, we have, a bunch of machine crystals, so should be able to do so.
But you measured the.
But at the moment, we don't have kind of any data. Yeah, and spin case, there are, number of inelastic neutron scattering, data, and they do see, quite, complicated, spin fluctuation.
Hi. Very interesting. In fact, I found a lot of similarities with B2O3 we discussed yesterday. But what I was wondering, why for magnetite, it actually charge orders, even though at certain temperature, but for lithium vanadate, it doesn't. Is it because that's inverse spinel versus normal spinel? Because that's an inverse spinel. This
Yeah,
is
of course, unlike, the B2O3, remember, we are working on the frustrated pyrochloride. And then if no charge order, spin channel is kind of frustrated. Okay, and in fact, in a charge order state of thin film, we did, this lithium, beta NMR technique, and we did see, magnetic ordering there. So like, so associated with kind of charge ordering, magnetic order kind of induced. So perhaps, charge ordering is kind of isotopic object, and they kind of, suppress, frustration in the magnetic order count. Yeah. Yes.
It's great to see a lot of progress in this topic, but what so I see the Hunts included in the models that you cited. One of the elements that's really important in rust and magnetite is the close interplay of slow phonon modes with the charge modes.
Yeah.
And this seems to be missing in the models that your friends have presented to us. And so should we as theorists go home now because your beautiful DMFT friends have solved the entire problem? Or are there elements that you feel are missing from the picture? Which is it?
Yeah, of course, yeah. No,
what is missing, or is it perfect?
No, yeah. I got your point. And of course, I spoke with Antoine, and he tried to develop charge ordering based on that. Yeah, and but somehow their model kind of missing lattice part. So he said he can reproduce kind of a charge ordering we observed, but some other kind of charge order. But I told him, don't worry, you are missing kind of lattice, and perhaps in future, they must incorporate lattice.
So when you have slow phonons, the physics of heavy fermion systems transforms very rapidly, and in particular, it can lead to a frozen state, a very anisotropic Kondo state, in which the timescales just diverge. And that's what causes rust. And so it seems that you must be very close to the transition between rust, totally frozen valence fluctuations, and condo or mixed valence. You're very close to that border here. So it seems that I would guess that when you include the
No,
photons to the Hund's picture, you get a more complete description.
So, but may I understand you, you're saying something like, polaric.
Yeah, absolutely.
yeah.
Yes. I think that's a really
Yeah,
important.
of course, that is very important. And
Yeah.
of course, child ordering kind of, stabilized, by kind of lattice, distortion. And it's clear, soft phonon, must be kind of around in
You kind of
yeah.
transform from
Yeah.
positive U, condo-esque, to negative U, but it's what's known as a very anisotropic condo problem with very little transverse fluctuations. And that kills the condo effect, the strong polaronic coupling. This must be very close to the point where it transforms from one to the other.
Okay.
We should talk more.
Okay. Yeah.
Well, thanks very much, Hide. I was just wondering how robust is the geometrical frustration in the single crystal, and whether, because the strain that you've put on it with the film is quite large. So I'm just wondering, have you not yet done transport under applied strain to see at what point charge order starts to appear?
Yeah, that's actually, we tried it first, but somehow, my PhD student kind of keep failed and he cried. And so that's why we moved to thin film instead of this.
So you saw no
direct.
effect?
Yeah, but of course, that in our mind, perhaps our technique is not good enough. Somehow crystal breaks and before, observing, charge order. So we haven't seen charge order yet.
Okay. Any more question? If not, then let's thank Professor Takagi once again.